Chapter 1. Setting the Stage. Coexistence and Where OpenLegacy Fits. Welcome back to the AWS Partner Skill Builder series. In our first session, we covered the business case for modernization, why these programs often get stuck at the integration layer, how OpenLegacy helps solve for that, and the kinds of outcomes customers like Bank Leumi have seen. Today, we're going one level deeper. We'll look at the architecture, show where OpenLegacy fits in an AWS mainframe modernization program, walk through a live demo, and share practical guidance you can use with customers. Jordan, before we jump into the product, help us set the stage. How should our SI and GSI partners think about the modernization landscape?
Sure. The first thing to recognize is that mainframe modernization is rarely one big, single event. It's a set of decisions made workload by workload. AWS describes that as a disposition strategy. For each workload, you're choosing the modernization path that makes the most sense based on the business goal, the technical complexity, and the level of risk. That might be replatforming, refactoring, reimagining, or using augmentation patterns to extend and modernize while core systems stay in place. The reality is that large enterprises are usually doing several of these at once. For example, a bank might replatform some non-strategic batch jobs, refactor selected transaction processing services, and reimagine customer-facing channels, all while continuing to run against the same mainframe. And that's where things get complicated. These efforts all have to coexist. They have to connect back to core systems. They have to work within enterprise governance, and they have to do all of that without disrupting the business. That's where the integration layer matters, and that's where OpenLegacy fits.
And running multiple patterns at the same time is exactly where things get hard for the delivery team. How do you keep the business running while all of that transformation is in flight?
That's the core challenge. And it's why coexistence is not just a transitional phase. It becomes the operating model for a meaningful portion of any serious modernization program. A useful way to think about this is as two parallel factories working against the same mainframe estate. The first is the migration factory. That's where AWS Transform for Mainframe operates, analyzing dependencies, decomposing the monolith into business domains, and supporting the refactoring and migration work. The second is the integration factory. That's where OpenLegacy operates. OpenLegacy automatically generates APIs and integration assets that connect legacy systems to modern applications and cloud services. And the key point is this: these are not sequential motions. You do not finish one and then start the other. They run in parallel. That parallel operation is what allows enterprises to modernize in phases while keeping the business running.
So OpenLegacy is the integration factory. What does that mean in practical terms for a partner starting a modernization engagement?
It means you can begin from day one. You can start exposing mainframe business logic as APIs without waiting for the refactoring work to complete. The legacy system continues to run, and OpenLegacy generates the connection layer around it. Those APIs serve two purposes at the same time. First, they allow new applications and services on AWS to access legacy data and logic in real time. Second, they create an abstraction so the underlying implementation can evolve over time without breaking downstream consumers. That's the strangler fig pattern in practice, not as a future state concept, but as something that becomes operational early in the program.
And OpenLegacy supports more than one pattern within that coexistence layer. Jordan, walk us through those patterns, because this is what helps a partner scope the engagement correctly.
Exactly. At OpenLegacy, we typically describe these as decoupling patterns, the ways you safely separate legacy capabilities so modernization can happen in phases without disrupting the business. In AWS guidance, you will often hear the coexistence layer described in practical integration terms: application to application, application to data, and data to data. The language is a little different, but the architectural goal is the same: enabling legacy and modern environments to run side by side while modernization moves forward. So let's walk through those three patterns in practical terms. The first is application to application. This is where one application interacts with another through APIs or event-driven services. In OpenLegacy terms, this maps to exposing and connecting business capabilities safely across environments. OpenLegacy automatically generates APIs and reverse APIs where needed, so business logic can be invoked in and out of the legacy environment. The second is application to data. This is where an application needs governed access to data managed by another system. In OpenLegacy terms, this aligns to decoupling access to legacy data, so it can be consumed in a modern architecture through generated APIs. This can also be done in the opposite direction, where OpenLegacy generated reverse APIs enables legacy systems to access modern data. The third is data to data, and this is where data moves between platforms at the data store level. For OpenLegacy, this applies to specific legacy scenarios, particularly around stores such as IMSDB and vSAM.
Before we look at the hub itself, there's one foundational question partners always want answered first. Does any of this require changes to the mainframe?
No changes to core mainframe business logic are required. OpenLegacy connects to the legacy system and reads the existing metadata, things like COBOL copybooks, PCML files, and program definitions. From that metadata, it generates the integration layer. So you are not rewriting the legacy application just to expose it. You are generating a modernization-ready interface around what already exists. That principle is important for partners, because it means you can start creating value without first taking on the risk, delay, and disruption of changing the core system.
So if Chapter 1 is about where OpenLegacy fits in the modernization motion, the next question is, what is OpenLegacy Hub, and how does it actually work? Chapter 2, OpenLegacy Hub Fundamentals, what it is and how it works. Let's talk about the product itself. Jordan, for a partner brand new to OpenLegacy Hub, what is it at its core?
At its core, OpenLegacy Hub is a cloud-native, design-time platform that automates the creation of APIs and integration services from legacy systems, without requiring any changes to those systems. It connects to an existing mainframe or mid-range environment, reads the metadata that already describes the programs and data structures, and uses that metadata to generate production-ready services. What gets generated is standard modern low or no code that can be deployed natively into AWS environments, as containerized services or serverless functions, depending on the customer's architecture.
Let's look at the reference architecture so partners can see how the pieces fit together in an AWS deployment.
The easiest way to understand the architecture is to separate design time from runtime. The architecture has two distinct environments working together. At design time, you have the OpenLegacy Hub. That is where developers define connections, read metadata, configure the service, and generate the API or integration asset. At runtime, those generated services run in the customer's own AWS environment, for example, inside the customer's VPC. Depending on the customer's architecture, that may mean containerized services running on Amazon EKS, serverless functions running on AWS Lambda, with Amazon API Gateway in front of them. And then, of course, there is the customer's data center, where the mainframe or mid-range system continues to operate.
So the hub is the design time environment, and the generated services run in the customer environment. Walk us through how a new API gets created.
There are two flows partners need to understand: the generation flow and the execution flow. The generation flow is what happens when a developer creates a new service. First, the developer works in the hub to define the connection and select the legacy program or asset they want to expose. Second, the hub reads the metadata that already describes that asset. For example, a COBOL copybook, the PCML definition, or another existing program definition. Third, the hub generates the service that can be deployed into the customer's AWS target environment. The important point is that the output is standard low or no-code service. It deploys into the customer's chosen AWS architecture rather than into a proprietary runtime layer.
And once that service is deployed, what happens at runtime when a consumer calls it?
That is the execution flow, and it happens on every API call. A user or application sends a request to Amazon API Gateway. From there, the request is routed to the generated service, either on Amazon EKS or on AWS Lambda, depending on the deployment model. That generated service communicates with the legacy system through the established connectivity path, executes the interaction, translates the legacy response into a modern API response, and returns it to the caller. So from the consumer's perspective, they are interacting with a standard API. The complexity of the legacy protocol stays behind the generated service layer.
Jordan, which legacy systems does OpenLegacy Hub connect to? I want partners to understand the full scope.
The supported legacy footprint is broad. On the IBM mainframe side, CICS, IMS Transaction Server, IMS Database, DB2 for ZOS, vSAM, MQ, CICS Transaction Gateway, Batch Jobs, 3270 Screen Interactions, PL1 programs, and more. On IBM I or AS400, that includes RPG, PCML, DB2 for I, DataQ, MQ, and 5250 terminal interactions. Beyond IBM platforms, OpenLegacy also supports systems such as SAP, as well as industry-specific platforms like Hogan and Finastra in financial services. Across those environments, the generated output is standard modern code that can be deployed as containerized services or serverless functions in AWS.
There's one pattern worth calling out here because it often surprises partners and can be a real differentiator in a customer conversation. Reverse API.
Right. Most people assume modernization means cloud services calling into the mainframe. But OpenLegacy also supports the reverse pattern, where a mainframe application can initiate a call to an AWS-based service. A practical example would be a CICS program calling a risk scoring model running on Lambda, or another cloud-based service. OpenLegacy handles the protocol translation so the interaction works in the format the legacy application expects. For partners, that matters because the mainframe does not have to remain a passive endpoint. It can participate in new cloud-native workflows from day one. We'll come back to this pattern later, but it's important to recognize here because it expands what a coexistence architecture can look like.
So if we boil that down for a partner, the picture is pretty simple. OpenLegacy Hub is the design time platform. It generates standard integration services from existing legacy metadata. And those services run natively in the customer's AWS environment, connecting legacy systems into a modern architecture. That gives us the foundation. Next, let's look at deployment, security, and what a partner needs to have in place before implementation begins. Chapter 3: Deployment, Security, and Prerequisites. Jordan, let's talk about how partners actually bring OpenLegacy Hub into a customer environment. What are the deployment options, and how does a partner choose between them?
There are 3 deployment models, and choosing between them is one of the first scoping decisions in an engagement. The first is SaaS. In this model, the Hub design time environment is fully managed by OpenLegacy and accessed through the browser. The generated services still deploy into the customer's own AWS account. This is usually the fastest path and good fit for customers that are comfortable with cloud-managed tooling. The second is Enterprise. In this model, the Hub is self-hosted inside the customer's own VPC. This is typically the right fit for regulated industries, where the customer requires the platform to remain fully inside its own controlled network boundary. The third is Hybrid. That combines a managed design time environment with a private runtime inside the customer's own VPC. It gives customers the speed of the managed Hub while keeping runtime execution inside their private environment. So in simple terms, SaaS is usually the fastest. Enterprise is the most restrictive from a hosting perspective, and Hybrid sits in between.
For partners working with regulated customers, a government agency or Tier 1 bank, for example, what does that private deployment model look like in practice?
In an enterprise deployment, the Hub is deployed into a private subnet inside the customer's VPC, with no public IP addresses assigned to the Hub instances. For connectivity back to the legacy environment, AWS Direct Connect is typically the best option for production, because it provides a dedicated private connection between the AWS VPC and the customer data center. For a proof of concept or non-production environment, a VPN connection can also be a viable option. The exact network requirements, including ports and connectivity details, are customer and implementation specific. Those are defined during delivery by the network team and legacy system administrators based on the customer's environment and security policies.
Let's talk about security, because that is usually the first question from the mainframe and infrastructure teams. How does OpenLegacy access the legacy system without introducing new risk?
There are really 2 parts to that answer: API layer security and legacy system access control. At the API layer, OpenLegacy supports the same kinds of modern security controls architects expect in cloud-native environments: TLS and mutual TLS for transport security, JWT and OAuth 2.0 for token-based authentication, and RBAC for role-based access control. At the legacy system layer, OpenLegacy works within the security boundary that already exists. In RAC-F-controlled environments, for example, access is still governed by the mainframe's own controls. OpenLegacy connects using the service account and permissions the customer explicitly grants. There is also an important control at the metadata level. OpenLegacy uses a project package, or OPZ, which defines exactly which programs the runtime is allowed to execute and how inputs and outputs are structured. That means the runtime is operating within a defined contract. It is not browsing the mainframe, and it is not issuing arbitrary commands. It is executing only the transactions and interactions that have been explicitly defined in that package.
And what about credentials? Where are those handled?
Credentials for the legacy environment are not stored in the metadata or hard-coded into the generated service. They are stored in AWS Secrets Manager, and the runtime uses a scoped IAM role to retrieve them dynamically at execution time. That supports credential rotation, aligns with least privilege access practices, and keeps sensitive connection details out of the project definition itself.
Partners in regulated industries such as banking, insurance, and government are also going to get questions about compliance. How should they handle that conversation?
The practical way to frame it is this. OpenLegacy generates services that then act as an integration layer. Its role is to connect systems and pass data between the legacy environment and modern applications. Because of that architecture, the primary compliance responsibility typically remains with the systems that own, store, and govern the regulated data. The legacy platform on one side, and the customer's AWS environment on the other. OpenLegacy does participate in customer-driven security and compliance reviews, including providing supporting information such as vulnerability testing results when required. And for access to the hub itself, the control plane also has its own access model. The SaaS offering uses Auth0, and the self-hosted deployment uses Keycloak. The exact implementation details will vary by customer, but the architecture and control model stay consistent.
So from a partner perspective, the takeaway is clear. Choose the deployment model based on customer policy and operating constraints. Connect the runtime securely into the existing environment, and work within the customer's existing security and compliance boundaries. With that foundation in place, let's move from architecture into execution and look at what this actually looks like in a live app-to-app integration demo. Chapter 4, Live Demo. Get account information end-to-end. We've covered the architecture and the coexistence model. Now let's see what this looks like in practice. Jordan, set the scene.
In this demo, we're taking a real COBOL program running on CICS mainframe and exposing it as a REST API. The mainframe program stays completely unchanged. We'll do this in two phases. First, we define the module, which is the legacy connection. Then we create the project, which is the API service. Let's start. We start in OpenLegacy Hub by creating a new module. In OpenLegacy, the module defines the legacy connection and the asset we want to expose. I click Create Module. The hub shows every connector it supports. I'll filter by mainframe. You can see the options: CICS, IMS, DB2, vSAM, MQ, and more. For this scenario, we select Mainframe CICS COBOL. I name the module and provide the connection details, the address of the CICS system, and the URI map. These come from the mainframe team, no code to write. Now I add the asset, the specific program we want to expose. The hub gives two options: provide a copybook or provide the full COBOL source file. We use the source file here and upload it. The hub parses the file automatically and extracts the full data structure. Every input field, every output field, every data type. I didn't define any of this. It came from the existing COBOL program. Before building the API, I run a quick validation. The hub generates a test case automatically. I enter an account ID and run it. The test passed. Real account data coming back from the CICS mainframe. Account holder, balance, currency, account type. The connection is working. The asset is validated. We haven't written a line of code. The module is done. That's the legacy connection defined and validated. Now we move to project creation. We enter the module and click Add to Project. We enter the project name, and next we choose the service type. You can see the options: REST API, serverless for Lambda, reverse API, event streaming, file processing, data patterns. We're building REST, so I select API or web service. Once the project is created, we generate the contract. The hub offers several options. You can upload an existing spec, use a template, build manually, or let the hub auto-generate it. Here we choose auto-generated, so the service is built directly from the asset definition. The hub generates the API method automatically. The method is called getAccountDetails, a get endpoint that takes an account ID. I open it and can see the flow. The request comes in, the CICS program is called, and the response goes out. This was all built from the asset definition, not hand-coded. Watch this. The credit card number is in the output. But before this API returns data to any consumer, I can apply a masking rule directly in the flow. One click. The field is masked. No code written. This is how data governance gets added at the API layer. We then add an expression step to handle a simple transformation on the account ID. Here we use the built-in AI capability. We describe the requirement in natural language. The hub generates the logic. We review it, validate it, and save it back into the flow. This is an important point for partners. The generated service is not just a wrapper. The flow can be enriched before deployment. Now we switch to the test view and validate the API end-to-end. The response comes back with the account data, the credit card number masked, and the account ID transformation applied. That confirms the method flow is working as designed. From there, we deploy the service to AWS. The deployment generates the service and its OpenAPI specification. After deployment, we authorize the service and perform a live test. We receive an HTTP 200 response, along with the returned account data from the service. That is the end-to-end result, an existing CCS COBOL program exposed as a REST API, enriched in the flow, and deployed into AWS, without changing the mainframe business logic.
That's the complete picture. From a tightly coupled COBOL program that only the mainframe could reach, now exposed as a governed REST API in AWS. The important takeaway is not just speed, it's the operating model. The legacy program stays in place. The API is generated from what already exists, and partners can add policy, transformation, and security before deployment. The same workflow applies to any legacy system OpenLegacy supports: CICX, IMS, DB2, RPG on IBM i. The connector changes, the process doesn't. Before we move on, Jordan, one question partners always raise at this point: how does OpenLegacy fit into an existing CI/CD pipeline? Can this whole workflow be automated?
Absolutely. OpenLegacy integrates seamlessly with CI/CD pipelines by exposing its full lifecycle through a powerful CLI, enabling complete automation without relying on the UI. Teams can script the creation of modules, including connector type and connection details to back-end systems, and automatically generate assets from sources like COBOL copybooks. This ensures consistency, repeatability, and alignment across environments while reducing manual effort and errors. The CLI also supports automated creation of projects and generation of services, which can be built and validated as part of the pipeline. Generated unit tests can be executed directly within CI/CD workflows, acting as quality gates before deployment. This allows teams to continuously verify that integrations behave correctly as changes are introduced. OpenLegacy also enables API-level test case creation, allowing simulation of real-world service interactions. These tests can be scheduled or triggered within the pipeline, supporting continuous testing and monitoring. Overall, this automation-first approach allows organizations to embed legacy integration into modern DevOps practices, improving speed, reliability, and consistency across the delivery pipeline.
Chapter 5: Coexistence Patterns in Practice. Let's bring everything back to the broader modernization journey. In a real customer engagement, partners are rarely dealing with just one integration scenario. So Jordan, how should they think about coexistence in practice?
The first thing to remember is that coexistence is rarely a temporary technical bridge. In most serious modernization programs, it becomes the operating model for a meaningful period of time. That is because modernization does not happen in one neat sequence. Different functions move on different timelines. Some are being refactored, some are being replatformed, some are being reimagined. And while all of that is happening, the business still has to run. That is exactly why the coexistence layer matters so much. It is what allows old and new environments to operate side by side, while transformation work continues in parallel. And in practice, partners usually see that layer expressed through three integration patterns: application to application, application to data, and data to data.
So let's walk through those patterns from a partner point of view. How do they actually show up in an engagement?
In practice, all three can appear in the same program, often against the same mainframe estate. The first is application to application. This is usually the most immediate pattern. A new digital channel, cloud-native service, partner API, or internal application needs real-time access to mainframe business logic. That is where generated APIs and reverse APIs become important. They let modern applications call into legacy logic, and, when needed, let legacy applications call out to modern services. We demonstrated that app-to-app pattern in Chapter 4. The second is application to data. This is where a modern application needs governed access to data that still lives in the legacy environment. It might be a cloud service reading customer or policy data, an analytics application consuming operational data, or a modern workflow writing updates back into a legacy managed store. In those cases, OpenLegacy exposes that data through generated interfaces, so it can be consumed in a controlled, modern architecture. The third is data to data. This is the pattern partners use when data itself needs to move between environments at the platform level, so that the data modernization workstream can progress in parallel with the application workstream. For OpenLegacy, this applies to specific legacy data scenarios, especially around stores such as IMSDB and vSAM. So from a scoping perspective, these are not just architecture labels. They help a partner decide what has to be exposed in real time, what data has to be made accessible, and what data movement has to happen in parallel with broader transformation.
And where does this sit alongside AWS Transform for Mainframe? Because many of our SI and GSI partners are going to encounter both in the same engagement.
This is one of the most important points for partners to understand. AWS Transform for Mainframe handles the transformation work. That includes analyzing complexity and dependencies, decomposing the monolith into business domains, planning migration waves, and supporting refactor and reimagine paths. That is the work of changing and moving functionality over time. OpenLegacy, as an integrated part of Transform, handles the integration and decoupling layer that makes coexistence operationally viable while that transformation is in progress. We expose existing logic and data through APIs, manage the traffic between mainframe and cloud services, and preserve the integration contract while the underlying implementation evolves. So the practical result is this. Cloud applications do not have to wait for the refactoring work to be complete before they can start consuming business capabilities. They can begin using those capabilities through OpenLegacy generated interfaces from day one. Then, as those underlying services are modernized and moved into AWS, the consumer-facing contract can remain stable. The implementation changes underneath, but the consuming applications do not have to be rewritten each time a workload moves. That is the strangler fig pattern in practice. Transform, coexist, eliminate. With AWS Transform driving the transformation path, and OpenLegacy making the coexistence phase workable at enterprise scale.
So if AWS Transform is changing the application over time, OpenLegacy is keeping the business connected while that happens. Let's make that real with an example under genuine business pressure. Jordan, walk us through the large insurer story.
This large insurer is a strong example because it shows that this model is not theoretical. It shows what phased coexistence looks like under real enterprise pressure. They needed to separate ancillary and surrounding services from the mission-critical COBOL estate, modernizing those surrounding workloads while keeping the core system stable on the mainframe. A major bottleneck in that environment was CTG, the CICS transaction gateway. It was both a cost issue and a coupling point. OpenLegacy bypassed that layer by connecting directly through the CICS adapter and auto-generating APIs from the existing COBOL programs without changing the business logic on the mainframe. From there, they made deliberate workload placement decisions. Steady, predictable workloads were placed on OpenShift running on Amazon ECS. More variable, spiky workloads, especially in claims-related scenarios, were placed in a serverless AWS Lambda environment where they could scale elastically. Both sets of services were generated from the same legacy estate and connected back to the mainframe system of record through the OpenLegacy API layer. That is the key lesson for partners. Coexistence is not just about keeping the mainframe connected. It is about making smart workload placement decisions for different workload types while modernization proceeds in waves. The mainframe remains the trusted system of record. New services run in the right cloud environment for their behavior and scale profile. And the integration layer keeps the whole architecture operating as one system while the transition continues.
That's an important distinction. This is not coexistence for coexistence's sake. It is coexistence with deliberate workload placement, stable interfaces, and a clear path to keep modernizing over time. So if you're a partner working through this, What is the practical takeaway?
The takeaway is that coexistence patterns are how you operationalize phased modernization. They help you decide which business capabilities need real-time exposure, which data has to be made accessible, which data movement needs to happen in parallel, and how to keep legacy and cloud environments working together while broader migration continues. That is why the integration layer matters so much. It is not a side concern. It is one of the things that determines whether a modernization program can move in phases without disrupting the business. And that is where OpenLegacy fits, as the integration and decoupling factory that runs alongside the migration factory from day one.
So at this point, we have covered the architecture, the hub fundamentals, the security and deployment model, the live API generation flow, the testing and DevOps integration, and the coexistence patterns that make phased modernization work in practice. In our final chapter, let's make this actionable and talk about how partners get started. Chapter 6: Getting Started and Partner Next Steps. We've covered a lot of ground today. Let me close with the practical question that every partner asks at the end of a session like this. How do we actually get started?
The first step is to register and access the OpenLegacy Hub SaaS environment at app.ol-hub.com. Anyone can register and immediately start working in the design time environment, defining connections, parsing metadata, and generating services, without any infrastructure setup. It's worth being clear about what kind of platform this is. OpenLegacy Hub is a development platform. All the work we demonstrated today, the API definition, the metadata parsing, the method flow composition, the service generation, happens in the hub. The generated services then deploy into the customer's AWS account. There is no traditional product sandbox to access because the hub itself is the development environment. For partners who want to validate the full end-to-end deployment, the generated services running in a real AWS environment connected to a legacy system, that validation is done by installing the enterprise model in your own AWS account and connecting it to a lab or test legacy environment. For structured training before you start, OpenLegacy has training materials in development, accessible through app.ol-hub.com once you've registered. These are being actively updated. Reach out to the Partner Alliance team to understand what's currently available and what's coming. For a structured first engagement with a real customer, we recommend a 4-step approach. First, a discovery call, an initial assessment of your customer's modernization goals and their current mainframe landscape. Second, a scoping analysis workshop, a half-day session to identify high-impact integration candidates and define the target architecture. Third, a tailored demo and ROM, a 2 to 4 week exercise using OpenLegacy Hub to demonstrate fit against the customer's actual programs, optionally combined with AWS Transform for mainframe. Fourth, a roadmap and business case, a modernization scope plan with projected timeline and TCO analysis. The downloadable resources in the video description give you everything you need to prepare for those conversations. The solution brief, the reference architecture diagrams, and the Getting Started guide.
And Jordan, there's something specific about the commercial model for SI partners that's worth knowing before we close.
OpenLegacy is a part of the AWS Migration Acceleration Program, which provides funding to offset license costs for qualified modernization projects. Critically, this funding is in addition to the MAP funds that SI partners are already using on AWS engagements. It doesn't compete with your existing MAP allocation, it adds to it. For GSI partners specifically, that means the commercial model for including OpenLegacy in an engagement is highly favorable. Engagement velocity goes up, license cost barriers for the customer come down, and the delivery efficiency we've demonstrated today translates directly into improved project margins.
To close, what we've covered today is the complete picture of how OpenLegacy operates within an AWS mainframe modernization program. The integration factory that runs alongside your migration work from day one. The 3 integration patterns that describe how your systems communicate throughout the coexistence phase. The hub that generates those integrations from existing metadata without touching the mainframe. The security model, the deployment options, the testing and DevOps integration that make this production ready. For your customers, this is what zero downtime modernization looks like in practice. For your practice, this is a repeatable delivery model with clear commercial incentives. Thank you for watching the AWS Partner Skill Builder series.